mentioned, my name is Philpp Thies. I'll give a brief sketch of the reliability challenges that I see for offshore renewable energy and some examples of what we do in terms of research. So, brief whiz through the context and challenges, and then I'll actually make it quite vivid, giving you an example of a dynamic marine power cable, and some more detail to the component testing that we're currently doing and that we're planning to do. So why are we interested in that, and why should we worry? First of all, it's a big opportunity. Blue growth is what is, on the European perspective, being labelled as the opportunities for wave, tidal and offshore wind energy, so everything offshore that provides us with electricity. From the UK perspective, we're seeking energy security, we're seeking to meet the carbon emission targets, and we're also looking for employment as a driver. So if you look at the left side on those two graphs there, that's the objectives and the target numbers given by DEC. And it's a reality, and we're actually not basing a great deal about it in the UK, but about 3 gigawatts of offshore wind is already installed. So the UK actually is a world leader in offshore wind energy. And it is a reality that about just shy of 5% is already being provided through offshore wind. The targets are really ambitious, so if you look at 2020 and 2050, we look at more than half of electricity will hopefully be provided through offshore generation means. On the European world perspective, there's different scenarios modeled on the different uptakes of the technology, but it has potential to be a large exporting industry for the UK, potentially worth up around the 40 billion pounds worth of GDP for the optimistic scenario. That is. You might have followed some press on prices, and that the government is really keen to bring those prices down. Because we're going offshore, we haven't really been there with those technologies yet. They are expensive, or more expensive than the conventional technologies, and especially offshore wind. So that's the left graph you see there. Offshore wind has been forecasted quite optimistically, and the first deployments have actually shown that the costs come in somewhere on the 140, 150 pound megawatt hour mark, which is about a third too high. So the government really tries very hard to push it down to 100 pounds a megawatt hour. Again, there's different scenarios and different learning curves to achieve that. For wave, which is much less mature, it's a very novel technology. We're talking about 400, 500 pounds a megawatt hour, maybe even more for the very first installations. But again, if you look at the strike prices, we're looking somewhere at the 150 pounds per megawatt hour target in the long term. But you can also see that the actual deployment to achieve those goals is in the significant gigawatt range, 15 plus gigawatt. The interesting thing for that research we were doing, or my research in particular, is that those reductions are not just plugged out of thin air, they're actually being matched up with figures, and about a quarter of those reduction in costs comes from reliability improvements. And a lot of those reports you just find, oh yeah, we'll just improve the reliability, but that's actually not a lot of ways of how to do it. So that's largely where my research comes in. The general offshore reliability experience from what I've been doing for wave energy, you can typically see 3 failure categories. And there's classic under-engineering, where you just underestimate the fact that you're going to sea, so you're not marinizing your application enough. And that's sometimes naive failures, but they still do happen. Then there's overlooked failure modes, where you've done a detailed analysis, but you may overlook failures. The recent examples are, for example, you might have followed in offshore wind, they've had problems with the actual grouting in the connection pieces, so that's been overlooked because that's been certified and it's been very detailed looked at, but they've overlooked that. And then there might be unexpected failure modes, which you typically get in new applications. The challenges though for those categories are that because there's a lack of field experience, there's typically very scarce data on failure rates if those load applications. But given those two, the reliability is still key to govern the actual project viabilities, because if your system isn't operating, you won't generate income, and any offshore intervention to repair and maintain your systems are almost prohibitively expensive. Where do we get the answers from, though? So 4 areas that we're looking at is general system modelling in terms of reliability, a basin updating procedure, which is always helpful if you're looking at a scarce data situation. We do a lot of numerical modelling, and I'll show an example of that, and we focus on component testing. So one example I've given you to make it a bit more tangible is the application of dynamic marine power cables, and that's actually quite a hot topic at the moment with offshore wind as well. Because what has been happening is that, so the dynamic marine power cable, I should probably explain, that's the part that connects any floating application with a static marine cable that's laid on the sea floor. So connections. And the usual applications in oil and gas on the left top hand side there, rather large structures. There's not a lot of motion happening, so those dynamic cables are being specified for these applications. If you look at the right hand side, and if you've seen anything about wave energy, these are typically a lot smaller, they sit in high energy environments, and they're sitting in the waves. And that's actually interesting to know. If you look at the left hand side, what offshore oil and gas typically tries to do is either they try and stay well above the waves, and that's all those raised platforms you can see, well above the waterline, or they stay well below, where there's less wave action. With the wave energy converters and some of the offshore wind, we're actually sitting right in that. So some of the modelling we've done was using tank tests to actually run a numerical model to see how does such a cable behave if we attach it to a wave energy device. And some of the results were that a typical catenary configuration, as you tell it as a default for oil and gas, is not at all suitable because the allowable tension is very quickly exceeded for moderate sea states. And so that's the top left-hand plot you see there. And at the other end, at the touchdown point, so where the cable reaches the bottom, you'll have compression there, which is very detrimental to the cable as well. So that configuration is not suitable at all for wave energy application. Something called the lazy wave, which is the plot on the right-hand side there. You can see that S-shaped form, where you have some floating bodies connected to the center of the cable, which lifts the center of the cable up. That lazy wave is for the same sea states, reduces the peak tensions quite significantly. We're down to 25 kilonewtons, so we're well within the allowable tension. But you buy that in the trade-off that you'll have local peaks just before and after the buoyancy sections, so you get some localized peaks there. But in terms of tension, the lazy wave is absolutely suitable. However, if you look at the fatigue, which is one of the governing failure mechanisms of concern for offshore renewables, very quickly they exceed the limits of the copper conductors within the cable would be exceeded with a standardized or with a normal cable. So we're currently looking at an industry-funded PhD project to redesign that cable to optimize the properties. So that's for cables, but the kind of theme is the same for a lot of the research applications that we have. Is, do we need new components, or can we use existing components for those offshore applications? And if yes, how do we need to modify or adjust for the different environment? In order to assess that, we have, in my research, quite a focus on component testing, which is currently done in a lot of industries. And if you list the possibilities around, you can have either full-scale structures, which is typically done in the automotive or the aviation industry, or you can only test small-scale models at earlier stages of development. In terms of accuracy, if you do field testing, that's ideal, and then it goes down to scale to computer simulations. However, both cost and complexity go up with that list. So if you're looking at full-scale structures in the field, it tends to be very expensive. typically too expensive for research application. So a lot of the component testing we do is actually at that middle level. So we're testing specimens as opposed to full-scale structures, and we tend to do those in the lab, although we do have some field test sites as well. How do we do that testing? The approach we take is surface simulation testing, which is to get the information from the operating profiles from the actual sites we're operating in. So if you start at the top right hand corner there, we'll pick a few operating sites, for example the Philpp Bay test site. We measure those operating profiles with wave buoys and HCPs to get the wave and current characteristics. And we then ideally have a device on site to measure the load conditions in those operating conditions, or that could be alternatively numerical models or tank tests, depending on what device developers have, what stage they're at. We then combine those two to get a representative load spectrum that we can replicate on the test rig. With that approach, we've also been working on a load life prediction tool, taking the time series from the field or from tank tests and try and infer what fatigue life we could anticipate for those different components. We tend to look at generic components which lend themselves to all floating structures, so for example moorings and power cables, rather specific partake of features. Just an example here from the test rig again with a marine power cable in. That rig is quite unique actually in the world, because we've taken the normal tensile test rig and extended it with what we call the moving headstock, which you see on the very right hand side of the larger picture there. And actually if you would stand in that rig and look down the headstock, you can just see the cable being mounted to that headstock. What that does, I'll show a video which will probably come in hopefully over to your side as well. We actually can articulate that moving headstock in 3 degrees of freedom. So it's those two gimbals that allow us to replicate the floating motions. And then on the far end side, which you can also see pictured as an inset there, we have a typical tensile load actuator to supply the inline tension as well. Fingers crossed that shows on your side. So that's the cable installed. Yes, that looks all right. You might see it's a bit stuttering at your end, but you can see those two axes. So that's been actually a time series that we played back from a numerical model where the cable manufacturer approached us and said, "Oh, we want to look. We want to see how the cable reacts to that load profile in reality, rather than the numerical model." So that's a typical dynamic power cable that we've tested there. Just see the armoring. Now you can see we can do quite some large excursions, so it's plus or minus 30 degrees on that headstock, and we can also adjust the test length. So it's quite a variable rig, and we've had quite a lot of interest and quite a few tests being carried out on that rig.
Philip, are we nearly there?
That's my last slide. Sorry, that's
Thank
my
you.
last slide. I'd like to jump through that. We also try to take the field data and develop those contours to inform fatigue life. So that might be of interest to colleagues. To sum it all up, really, there's recognised potential for offshore renewables, and I try within my research to develop tools to adjust the reliability, improvements of performance. And within the college, I would hope that there's certainly scope for interdisciplinary collaborations across the field of statistics and control and efficient computing to develop those. And then thank you very much. That's the slide to show that reliability improvements are possible, which is actually onshore wind, which came down from 4 within 10 years to less than a failure in a year. So thank you very much.
Okay, thank you very much.